Hello and welcome to this the 19th lecture in this physics of materials course that we are going through. In the last couple of classes we have derived the Fermi Dirac statistics. We have looked at the basis for which we why we needed to derive it, and then we went ahead and looked at the derivation of the Fermi Dirac statistical distribution. So, what we will do in this class is we have arrived at an expression for the Fermi Dirac statistical distribution. So, what we will do in this class is to look at that expression that we have arrived at and try to understand what are the implications of that expression. What does that expression imply, what is sort of taken into account there, what are some features of that expression that we can later look out for, and also get an understanding of how it relates to everything else that we have looked at earlier on, and in what ways we have come up with some additional aspects that we are capturing here which perhaps we have not captured earlier on. So, this is the general outlook of what we will examine through this class. Okay. So, we will begin by rewriting this Fermi Dirac expression, and then we will start our discussion from there. So, we designate the Fermi Dirac statistical distribution by using the letter f. So, f of E I we call it is given by 1 plus e power E I minus E f by k b t. Okay. So, this is the expression that we have come up with. So, to put it in words, this is the probability of occupancy of a state at energy level E I, and it is being given by this expression. We have 1 in the numerator and 1 plus e power, this E I is that energy level that we are looking at. Okay. So, therefore, as you evaluate this expression, the value of E I can change for every energy level. If you are going from 0 energy to let us say some very high energy level, for every energy level that you can select here to check for its probability of occupancy, that is the energy level that will show up here, E I. Then we have minus E f, E subscript f, which at the moment we have not really discussed in any great detail, except to say that based on how we have derived it, this value of E f is a constant for that system. Okay. It is going to vary from system to system based on what we are looking at, but for a given system this is a constant, this E f is a constant which we can utilize at that point in time. So, in this E I minus E f is a constant, E I is something that we can change for our calculation purposes. K b here in the denominator is the Boltzmann's constant. So, by definition it is a constant. So, that is nothing that there is nothing that we can do, it is a constant there, and T is the absolute temperature. Okay. So, in other words and that of course is a variable so to speak, in the sense that when we evaluate this expression we will do so at a specific temperature, right. So, in other words we will specify the temperature, and for that specific temperature we can evaluate this expression for a variety of energy levels. Then you can change the temperature and say, let us say we are starting at absolute 0, at absolute 0 we can evaluate this expression, or as the temperature tends to absolute 0 we can evaluate this expression, and then we will have something that we will see is the behavior of this expression. Then we can raise the temperature, and at a higher temperature we can again evaluate this expression and see how the behavior has changed. So, this is the general what should I say, the general way in which this expression works out in terms of what is it that we can change and what is it that remains constant, and therefore in what context we can actually evaluate this expression and expect to see some data corresponding to that expression. Okay. So, so this is the Fermi Dirac distribution function. Okay. So, this is the, and it is of course credited to the two people who have contributed towards coming up with this function. So, I will just briefly, we will also now we will make a plot of let us say as the temperature tends towards absolute 0, we will make a plot of this function for a variety of energy levels. Okay. So, on the y axis we have f of E, so at different energy levels, and this is the energy. Okay, so on the x axis we have energy, a variety of energy levels that we can look at. On the y axis we have that function, the Fermi Dirac distribution function for each corresponding value of energy that we are going to look at. I mentioned in this expression that there is a constant which we have not really looked at in great detail so far, but this constant is some energy value. Okay, so some particular energy value is what this constant is, and it remains fixed for that system. So in this plot we will just mark up one location of energy, and I have just arbitrarily marked it up here. It is just a schematic of what we are going to get. So I will just arbitrarily mark a location on the x axis and say that for some hypothetical system that we are examining, that happens to be the constant value of energy that corresponds to this constant here EF. Okay, so I will mark that up here as EF. Okay, so we have marked this constant EF here. All the other energy values are available for us, I mean these are the energy values available for us to do something and look at this expression. Now clearly, given that there is a certain value for EF, there are values of energy that are less than EF, and then there are values of energy greater than EF, and of course there is the value of energy equal to EF. So E, as you look at the energy value that you look up here, can take all of those values. Okay, so or at least we can evaluate this function. This function can be evaluated for energy values that are less than EF, equal to EF, and greater than EF. So this entire range of energy values we can evaluate, fine. So what we will do is we will look at this expression and see what it works out to as you evaluate it for different values of energy, and we are specifically looking at a situation where the temperature is tending to 0. So we are looking at a situation where the temperature is very nearly absolute 0 in our scale of temperature, fine. So when you have E minus EF and the energy, so we will start from our from the origin and move forward. So for all these values of energy before you reach EF, E is less than EF, right. So therefore if you write E minus EF, that is a negative quantity, fine, and it is a negative quantity divided by kBT, where T is tending towards 0. So therefore this quantity here, so E power EI minus EF by kBT, okay, tends towards 0 as tends towards 0 or yeah, it tends towards 0 when E less than EF and T tends to 0. E less than EF means this is a negative quantity divided by a value that is approaching 0 would mean this is tending towards negative infinity. So negative infinity means E power negative infinity will make it tend towards 0, right. So E minus EF by kBT will tend towards negative infinity when E is less than EF and T tends to 0, and therefore this quantity is E power minus infinity, is tending towards E power minus infinity. So that is 1 by E power infinity, which is 0. So therefore this quantity tends towards 0 when E is less than EF, and therefore and when T is tending towards 0. So under these conditions this is tending towards 0. So in your expression here this is tending towards 0, okay. So in this expression this term tends towards 0 as long as the energy value EI is less than EF and temperature is tending towards 0. So in the limiting case, when temperature is absolute 0, we will say that this is negative infinity, and therefore I am sorry, this exponential term up here is the one that is tending towards negative infinity. Therefore this entire term here is tending towards 0. Therefore the value of this function evaluates to 1 because this whole term becomes 0, right. So if you look at, if I just draw a line here, a dotted line corresponding to the value of EF, and on the y axis I have 0, I have let us just say 0.5 and 1, okay. So when E is less than EF, f of E is equal to 1, at t equal to absolute 0. So, so for all, and this is going to be true for all energy values, right. So regardless of the energy value that you pick here, as long as the energy value is less than EF, this description that I have just given you will hold true, that it is going to become minus infinity, and therefore this term is going to become 0, therefore this is going to become 1. So for all values of energy less than EF, the value of this function is going to be 1 when temperature is absolute 0. So therefore this function will show a behavior that looks like this till E equal to EF, okay. So till the temperature I am sorry, till the energy level EF is attained, you are going to have the function evaluate to 1 for all energy values less than E equal to EF at temperature being equal to absolute 0, right. So now if you look at energy values which are greater than EF, so greater than EF you have energy values that are greater than the value of EF, which means the numerator here is now positive divided by a value that is 0. So therefore this value up here tends to plus infinity, and therefore this itself tends to plus infinity, therefore this whole function tends to 0, fine. So e power ei minus EF by kBt tends to plus infinity right. So we have seen these two cases here. So this is it is tending to 0 when E is less than EF, and it tends to plus infinity when E is greater than EF, and when it is 0 the function evaluates to 1, when it becomes infinity the function evaluates to 0. So therefore for all energy values greater than E equal to EF, the function simply coincides with the x axis, okay, and at E equal to EF we sort of have a discontinuous change going from here to here, right. So the function in fact shows you a behavior. So this is at t equal to, so we just mark the temperature here, so at t equal to 0 Kelvin we have seen this behavior. We see that the function is simply 1 till E equals EF, it drops to 0 at E equal to EF, or it changes from 1 to 0 when you are at E equal to EF, and then remains at 0 beyond this value of EF. So this is the behavior of the Fermi Dirac distribution function, right. Now in fact if you evaluate this for a variety of different temperatures, you will find that we have now evaluated it for t equal to 0 Kelvin, we can evaluate this same function for a variety of different temperatures. What you will see is that as the temperature increases you will see a behavior that looks like this. Okay, so this is at some temperature T1 greater than so I will call this T0 which is 0 Kelvin greater than T0, and this is at some temperature T2 which is greater than T1. So as you get to higher and higher temperatures you see a change in this function, basically in this distribution what it is showing you is that it is equal to 1 up to some energy level, after that it begins to drop from 1 and gradually drops to 0, whereas at 0 Kelvin it abruptly drops to 0. The transformation from 1 to 0 is more gradual if you go to higher and higher temperatures. So that is the behavior that you see for this function as you change the temperature, fine. So this is how you see this Fermi Dirac distribution function and the way in which it behaves. Now let us get an understanding of this EF, because it is a constant. I just mentioned it to you as a constant, and we will see what it represents. We need to keep in mind that when we looked at the Fermi Dirac distribution, when we started the whole discussion on the Fermi Dirac distribution, we basically said that we are now looking at a situation where first of all at you have specific energy levels, and at each of those energy levels there is a fixed number of states. Okay, so that was a constraint which had not been in our discussion before prior to when we started this Fermi-Dirac distribution process. Okay, so or the function discussion of the Fermi-Dirac function. Before we started this process, we never placed any restriction on the number of states available at an energy level. Once one of the fundamental aspects of the whole discussion regarding the Fermi-Dirac distribution function was this idea that at a given energy level we do not have infinite states, we have a finite number of states, and therefore the distribution process has to in some manner keep track of or accommodate these number of states. More specifically, we also said that Pauli's exclusion principle applies, and therefore not only do we have a finite set of states, we also have a limit on the number of particles we can place on those states. Even prior to our discussion on the Fermi-Dirac distribution function, we might have considered a case where the number of states was finite, but there was no restriction on the number of particles you could place on those states. So even if you had one state, you could have placed a million particles on that state, right? Whereas now we have this discussion has progressed to a point where we are saying the situation we are considering or examining is one where we have a finite number of states at any given energy level, and we have this restriction that we can only put a finite number of particles on those states subject to the Pauli's exclusion principle. So in fact, if the state is has all the details in it, all the quantum numbers specified for that for each state, you can in fact put a maximum of only one particle per state. So we have those restrictions thrown into our discussion, and the entire distribution the derivation had this as a very fundamental idea and which we saw in the last couple of classes. So what it means is that if you actually arrange the energy levels, and in a realistic situation where we are saying that particles will generally the nature tends towards the lowest energy levels that it can attain, if you arrange the energy levels in increasing order of energy and you take a set of particles and you try to fill up these energy levels, what will happen is that you will first fill up the lowest set of energy levels, right. So let's consider this discussion to be occurring at 0 Kelvin, which corresponds to this straight line curve that I have straight line that I have drawn here, set of straight lines that I have drawn here, right. So it comes up to E equal to EF, drops and then goes to 0, stays at 0. So at 0 Kelvin you take all the energy levels that are available in the system, the lowest energy level and subsequently increasing higher number of energy levels, and you start filling up the particles subject to the constraints that are prevalent in the Fermi-Dirac distribution function, which is that finite number of particles will go on those states and not more than one particle per state. So when you do this, obviously since you have a finite set of states, if once you start filling up one particle per state, when you fill up all the states you are done. You cannot, even though you may have a lot of additional particles available with you, you cannot add any more particles to the lowest energy level. So E0 if you say is the lowest energy level, let us say hypothetically it has 50 states, and we place the restriction that you can put only one particle per state. Now once you put 50 particles at E0, even if you have a million particles still left that that are available in the system that you can then place at various energy levels, you do not have the option of placing any more of those particles in those 50 states. So once those 50 states are filled, you are forced to go to the next higher energy level. Please remember this is at 0 Kelvin. Conventionally we say at 0 Kelvin everything is at the lowest energy level possible, that the entire system is in its ground state, and we have had a tendency to think the ground state means the lowest energy level possible. Immediately our discussion shows us that the moment we assume that the system is following Fermi-Dirac statistics, the moment we say that the system consists of particles that are fermions which are following the Fermi-Dirac statistics, we are immediately faced with the situation that the ground state does not imply that all the particles are sitting at the lowest possible energy level in the system. Okay. What immediately happens is that there is a finite number of states, they get filled first, then you go to the next higher energy level E1, that will also have a certain finite number of energy states, they also get filled up. You go to E2, you fill the states at E2, go to E3, fill the states at E3 and continue upwards in energy level, right. So you keep filling, you go to the next higher and next higher energy levels and fill all the states available at those energy levels. Steadily you fill those states and you go higher and higher and higher in energy level. This is at absolute 0 itself, right. So we do not have the option of trying to take all the particles and placing them at E0, simply because they are fermions and they will themselves not permit you to do so, right. So therefore you cannot fit them all at E0, you are forced to use higher and higher energy levels even though the temperature is absolute 0. So when you do this, you also recognize that in a typical system, let us say in the kind of system that we are talking of, which is a set of free electrons present in a solid, the number of electrons we may have is a large number, right. It may be some 10 power 23 electrons or whatever per if you are looking at, or 10 power 28 electrons per unit volume per meter cube or some such number. It is a large number, that is true, but it is not infinite, it is also a finite number, right. So it is a large but finite number. So when you do this process of filling up states steadily from the lowest energy level and proceeding to higher and higher energy levels, you will eventually reach one energy level which you are which we will just for the moment designate as En, some as we start from E0, E1, E2, E3, E4, we reach some higher energy level En, E subscript n, where the last set of particles available in the system fill the states that are available in that system, okay, at En. At energy level En also there is a finite number of states, the last set of particles that you have available in the system, last set of fermions you have available in the system, fill that set of states. Once you have filled those set of states, you have now run out of particles, okay. So the system may have capability to go to even higher energy levels after En plus 1, En plus 2, En plus 3 energy levels may become available, may be present in the system, may be defined for the system, but you have now run out of particles. So therefore all the energy levels above En will now remain empty, okay. So we have seen that if you take a set of fermions and you start filling up energy levels, we will go from E0 up to some number En, energy level En, where you will now run out of all particles. So initially you start at E0, you will run out of states, you will go to E1, you will run out of states, you will go to E2, run out of states, continue this process till you reach En, where as you run out of states you also run out of particles, more importantly you run out of particles. So any energy level above En there are no particles available to fill those states, so they all remain empty. So this highest energy level that you fill, which I have now described to you as E subscript n, that highest energy level that you fill at temperature being equal to absolute 0 temperature, that highest energy level is now this value Ef. So En, which I used as a general descriptive number, so that you can just follow this series that we did, E0, E1, E2, E3, E4, that is actually this value Ef. So up to the energy level Ef, all the states that are available to you get filled, completely filled at 0 Kelvin, okay. So please remember this is at 0 Kelvin, this description I am giving you is at 0 Kelvin. So at 0 Kelvin up to the energy level Ef, the states get steadily filled. Therefore since all of those states are completely filled, the probability of occupancy of a state is 1, right, because if you have 50 states and you have 50 particles sitting in those states, with the rule that there can be only one particle per state, it means that you are guaranteeing that every state is completely filled. That is the meaning in saying that you have 50 states and you have 50 particles, and that is the only way you can be consistent with that description, that you have 50 states, 50 particles, and you are permitting only one particle per state. Therefore every state has to have one particle. Therefore if you are looking at the number of particles by number of states, you will have 50 by 50, which is Ni by Si, and therefore that is equal to 1, right. So you have 50 particles, 50 states, all of them are occupied, so probability of occupancy is 1. So therefore at the lowest energy level that you can go, whatever is the number of states you have that many number of particles, therefore probability of occupancy is 1. You go to the next, so if you mark up here E0, E1, E2, E3, E4 and so on, for every one of them you go to E1, the situation is exactly the same, you have a certain number of states, you have exactly that many number of particles, okay, and therefore probability of occupancy is 1. E2 it is the same thing, E3 it is the same thing, you continue all the way up to Ef, okay. Up to that whatever is the number of states available at those energy levels, they are all completely full. At Ef we sort of have a discontinuous change going from 1 to 0, you know, it abruptly changes from 1 to 0 and then from there on it stays at 0. So at Ef you have for the first time you actually run out of particles, you have a certain number of states and you suddenly run out of particles, you fill those, so the last energy level that you fill is then therefore this Ef. Above Ef you have states available in the system which may be defined for the system, but there are no further particles available to fill those states. Therefore whatever be the number of states, let us say there are 38 states, I am just giving you some arbitrary number, let us say there are 38 states possible above this energy level, at the first energy level that is available above this EF. Since there are 0 particles to fill those 38 states, the probability of occupancy is 0, it is 0 by 38 which is 0, right. So therefore the probability abruptly drops from a value of 1 to a value of 0 at temperature being equal to 0 Kelvin, fine. So therefore this is a very clear, it is very clearly visible how this function actually results in this distribution when temperature is equal to 0 Kelvin, and we are also able to see the meaning of this value EF. This E subscript F is the highest energy level that is occupied in a collection of fermions at 0 Kelvin. This E subscript F is called the Fermi energy, okay. So E subscript F is referred to as the Fermi energy. Okay. Fermi energy is defined, there are actually two definitions for it. The first definition is at 0 Kelvin. At 0 Kelvin it is the highest energy level that is occupied, okay. The highest energy level that is occupied at 0 Kelvin is defined as the Fermi energy, fine. So see, even though we need to keep this in mind, one of the things you need to understand about a couple more aspects about this distribution that I would like to point out. The first is that since we have a finite number of states, we are forced to use energy levels above the lowest energy level available in the system, okay. So that is point number 1, alright. At the same time, still nature would like to occupy the lowest energy configuration that is possible, therefore it tries to keep filling all the states as much as possible at the lowest energy levels that it is possible to fill. So only when you reach EF and you first run out of particles, all the particles occupy only up to EF, they do not occupy any energy level above EF at 0 Kelvin. So in the ground state of a set of fermions you find this kind of a distribution, a ground state being the state of the lowest energy that is possible to attain for that set of fermions, and therefore at 0 Kelvin, in that ground state you find this distribution that continuously it occupies all the states available to it till it runs out of states and runs out of particles, and therefore actually runs out of particles more specifically, and then it occupies as many states as particles and then finally runs out of particles, and that energy value is this Fermi energy value. So the Fermi energy is therefore defined as the highest energy level that is occupied in the ground state, okay. So therefore the highest energy level that is occupied when T is equal to absolute 0. So the highest energy level that is occupied in a set of fermions as the temperature is absolute 0 is then described as the Fermi energy level. So therefore if you take a set of electrons and you say that electrons in a solid are going to behave like fermions, you will find that this is true. You will find that they are going to have a set of energy levels available to them, and at absolute 0 they will fill all of these states up to a certain high value of energy, relatively high value of energy, and at that point they will run out of electrons, and that will then become the Fermi energy level. Incidentally, for a typical metal this is of the order of 2.5 electron volts, so of that order you are looking at values, okay. So we will look at that little later, but so that is the kind of number that you are looking at. So that is the first thing. The other aspect I want to alert you to now, which we will discuss a little later in greater detail, but I will simply alert you to this aspect right now, is that please note that this function f of E is the probability of occupancy, okay. It is not, it in fact does not tell you anything about the number of states available at that energy level. These are two different pieces of information, okay. Even in the description that I gave you so far, I kept mentioning that maybe there are 50 states at some energy level and all the 50 states are full. The next energy level may have some other number of states and so on. The point to remember is that as you change the energy level, the number of states that exist in the system may be different. This diagram gives you, if you are not careful, it gives you the misleading information or misleading idea that perhaps the number of states is the same at all the energy levels. That is not the case, because this function does not say anything about the number of states. It merely tells you about the probability of occupancy of those states. More specifically, let us say as a realistic system might have, a hypothetical system may have say 50 states at E0, may have 75 states at E1, may have 110 states at E2, may have 150 states at E3 and so on. So the number of states available at E0, E1, E2, E3, E4 etc. need not be the same and are typically not the same. In fact, in a general system it is not going to be the same, those numbers are not going to be the same, there is a certain pattern for those numbers, there is a certain function which tells us what those numbers are, which we will look at little later. So this plot here does not tell you any information about the number of states available in the system at any given energy level, it only tells you the probability of occupancy of those states. What is the difference? It simply says, I just said here as an example, let us say that E0 has 50 states, probability of occupancy is 1, it means there are 50 states and all 50 states are full, that is all it says. The next energy level E1 may have 70 states, again probability of occupancy is 1, that means 70 particles are on those states and therefore those states are full. The next one may have 100 states available to you, next energy level, all 100 are full because probability of occupancy is 1. So you have 50, 70 and 100 particles continuously filling those 50, 70 and 100 states that are available to you, right. So probability of occupancy is 1, that is the meaning of this function, it does not tell you anything about the number of states. If there are 5 states and probability of occupancy is 1, it means there are 5 particles there. If there are 1500 states and probability of occupancy is 1, there are 1500 particles there. So at every energy level there is an additional piece of information not captured on this plot, which is the number of states available to you at that energy level. Okay, so that is an information that has not been captured here. Okay, so that is an information we will add on later, and that is the more complete picture of what is there in the solid. This is only the probability of occupancy. So you need to know the probability of occupancy and the number of states at that energy level, to taken together that tells you the actual distribution of electrons in that system. Okay, so that is so the full information is not yet here, so that is something we should be alert to. This is simply the probability of occupancy. So when you continue in this form, you know there are 50 states, then 70 states, then 100 states, 1500 states, whatever, you may eventually reach a point where there are, I am just taking some arbitrary value of energy just above EF, and let us say there are 3000 states available at energy level just above EF plus 1 whatever. If we spoke of E0, E1, E2, En is EF, En plus 1. So the first energy level above the Fermi energy level, let us say hypothetically that there are 3500 states, probability of occupancy is 0, it means there are 0 particles sitting in those 3500 states, all those 3500 states are empty, fine. So that is so that is how the actual distribution in the system is going to be. So the number of states available at each energy level is a separate piece of information which we have not incorporated into this plot. We have only incorporated, regardless of the number of states available at that energy level, what is the probability of occupancy of those states. Is it 50%, is it 100%, is it 90%, that is the information that is available here. Okay. So we will do the complete picture a little later because we need to do some more calculations to get there, but this is a very important piece of the overall picture, so that is why we have focused on it. Okay. So this is what it is. So we have looked very carefully at what happens at 0 Kelvin. At higher temperatures what you see is that certain number of states very close to the Fermi energy level, the probability of occupancy actually decreases from 1, alright, and certain number of states which are at energy level above EF actually have a probability of occupancy greater than 0 compared to the what you see at 0 Kelvin. So if you actually make a plot of this at slightly higher temperatures and then you do this look at E minus EF and then you do this calculation, right, when obviously I mean when E is very small, this will still follow the same kind of behavior that we described. As E gets very close to EF on either side of EF, it will show you a slightly different behavior because this T is not exactly 0, T is actually finitely above 0 Kelvin, and then so this is a very small number but it is a non-zero number. So when you have a small number here and you have a small number here, this is not going to evaluate to either plus infinity or minus infinity. Okay, so you are going to have some finite numbers there. Because you are going to have some finite numbers here, this is also going to have numbers between 0 and 1. Okay, so that is how this function is going to change, and as the temperature changes to little higher and higher values, that effect of that range of energy values over which you see this gradual transformation from 1 to 0 is going to increase. So you see that at a small temperature just above T0, you see that the energy values over which this goes from 0 to 1 is actually here. Okay, so this energy to this energy. So in this range the values are going from 1 to 0, for example here. If you go to a slightly higher temperature, it goes from 1 to 0 in this range of energy values. So in this slightly larger range of energy values the transformation goes from 1 to 0, okay. So what it means is that if you compare with respect to EF at values of energy which are less than EF, you have a probability of occupancy that is little less than 1, and at values of energy greater than EF you have probability of occupancy greater than 0. So this is the kind of distribution that you see for coming out of the Fermi Dirac statistics as a function of temperature now, okay. So as a function of, we have seen as a function of energy, these different curves are as a function of different temperatures, right. So that is what we are seeing. Again even in these additional cases that I spoke of, which is at T1 and at T2, this picture is not telling you anything about the number of states, okay. So I will just arbitrarily state that, you know, let us say there are this is let us say this is 0.8, okay. So all it says is that at this energy level the probability of occupancy is 0.8. So if there are 100 states available at that energy level, there are 80 particles sitting in those 100 states. That is basically all the information that is captured in this plot. So now I said that at temperature equal to 0 Kelvin the highest energy level state that is occupied is the Fermi energy level, okay. So Fermi energy we will define it is the highest occupied energy level at 0 Kelvin, and at the same time, or the other description, at temperatures greater than 0 Kelvin at any temperature greater than 0 Kelvin, when energy is equal to EF, E equals EF. If you look at this plot here, when T is not equal to 0 and E equals EF, okay, if E equals EF, this E minus EF is going to be 0, okay. So E minus EF is 0 divided by a non-zero quantity, so that is still 0, so E power 0 is 1, okay. So therefore this f of E will evaluate to half, okay. So 1 by 1 plus 1, this term will become 1, E equals EF, this becomes 0, so this whole thing remains 0, therefore this term becomes 1, so this f of E will become 1 by 1 plus 1, which is 1 by 2, so it is half, okay. So at any temperature greater than 0 Kelvin the f of E will equal half when E equals EF. So these are the two definitions for the Fermi energy. Fermi energy can be defined at 0 Kelvin as the highest occupied energy level at 0 Kelvin. It can be also defined for any other temperature as the energy level where the probability of occupancy is half, okay. So in fact I have sort of deliberately drawn it that way without highlighting it so far, now we will highlight it. If you take we have written f of E as 0, 0.51, those are 3 points I have highlighted, I just put in a 0.8 here. So if you just draw this 0.5 line at all temperatures greater than 0 Kelvin, you will find that as the probability of occupancy changes, it will go through 0.5, it will go through 0.5 when E equals EF. So at T1 also it goes through 0.5 when E equals EF, at T2 also it goes through 0.5 when E equals EF as you go through all the energy levels available in the system, right. So this is the manner in which this process is occurring, right. So that is how the Fermi Dirac distribution is present within this is manifesting itself, that you have all these energy levels, as you change the energy level you have this behavior. The Fermi energy is simply the highest energy level that is available in the system at 0 Kelvin, and it is a energy level where the probability of occupancy is 0.5 at any other higher temperature, okay. So that is the thing, and also as I mentioned again I will once again mention that this diagram does not tell you anything about the number of states available in the system. Now which is the other piece of information that we will look at later. What I also want you to understand from this picture is that when you have a set of fermions and you fill them up, the kind of physical analogy that you can think of is very simply that you have some kind of a container in which you are filling items of some category. Okay, so let us just say you have a container and you are putting sand in it, right, or water in it, whatever, sand or water, whatever it is that you are pouring into it. The containers has only finite space at the lowest energy or the lowest height that you have in the container. So as you pour water or sand into it, it fills up from the bottom and moves upwards till you reach the top of till you run out of sand or water, assuming that the container is a very large long container which in which you can put how much ever which is larger than the amount of sand or water that you have. Okay, so you start pouring it in, it will start filling up from the bottom and moving upwards, then eventually you will run out of sand or water. Okay, so therefore there is a highest height and therefore a highest energy level for the sand or water that you pour inside that container. This is the exact analogy to the system that we are looking at. Okay, we have energy states available in the system, from a lower energy state to a higher and higher energy states. You start pouring electrons, so to speak, in a descriptive sense you are pouring electrons into those states, they start filling up from the lowest energy level that is available to you to higher and higher energy levels, eventually you run out of electrons. So there is a certain number of there is a certain highest energy level state that is available to you, and up until that state all the possible up until that energy level all the possible states that are available are completely full, okay, are completely full, and therefore the probability of occupancy is 1. Above that energy level or above that height, as long as the system is undisturbed and stationary, you do not have any further states that are occupied, and therefore the probability of occupancy is 0. So that analogy that I described to you captures this information that I have just shown to you as the Fermi Dirac distribution. The information that is not captured in this picture, which I kept talking of in terms of the number of states, so to speak, is to, if you look at the analogy that I just described of some container in which you are filling up this water or sand, the information that is not captured in that is the shape of that container, right. So I could have a container that looks like this, I could also have a container that looks like a pot. Okay, in this container the number of the width of this container is constant. So in terms of my analogy, if I am pouring sand or water into this, the amount of sand that is held at the lowest energy level is the same amount of sand that is held at the next higher energy level or the next highest height, and so on. The amount of sand that I am holding at all these heights is exactly the same. So I might run out of sand somewhere here in this case, right. So the number of sand particles, if the sand particles were all very uniform and the way they were sitting was all uniform, if all that were true, the amount of sand that I could hold in this lowest height would be the same as the amount of sand I could hold at any other arbitrary height above it, okay, at that given height, a given location. That is not true in this container. This container has a different shape. It is still filling up the container, the logic behind filling up the container is still the same. Whatever initially I pour some sand into it or water into it, if there is only so much sand, it will just fill up the lowest available height in that container, and it will just fill that up and it will stay there. So again the probability of occupancy of the locations below that height is 1, because the sand is fully filled up to that point. Above it there is no sand available, it is all 0, but you can fill more and more sand. Let us say I take the same amount of sand and fill it up, it may come up to this height in this container. Sand or water, whatever it is that you have filled here, will now come up to this height in this container. Okay, so therefore the probability of occupancy, so this container is full up to this point, so whatever space is available is all occupied by that sand or water. Okay, so there is no empty states. We assume that the sand particles are able to pack themselves up very well, there is no gap between them. That is a hypothetical case. So maybe a liquid is a better analogy, we can more easily visualize no space being there between the liquid molecules, at least from our perception of the liquid. So we are just filling up all those locations. So it is fully occupied, fully filled in positions below this highest height level and fully empty above this height level, and this highest energy, so there is a corresponding highest height here or highest energy level that we can talk of. Okay, so the Fermi energy that we described is analogous behavior in a set of fermions or electrons which are trying to fill, instead of a container, a set of energy states available in that system. In that kind of a situation, this is exactly what is happening. So you fill up all the energy levels up to this point, right. And in simply talking of the f of E distribution, all it says is that f of E is 1 up to this point and it is 0 beyond it, if you want to look at the energy. Similarly, f of E is 1 up to this point, it is 0 above this. So in both these cases, the general idea is still the same, that the probability of occupancy is 1 up to a certain point, and then the probability of occupancy drops to 0 above that certain point. What significantly differs, even though the number of let us assume I put the same amount of water in both these containers, okay, what is significantly different about these two pictures is that since the shape is different for these two containers, and therefore the number of states, so to speak, or the number of locations in which you can place water at the lowest energy level is only so much here, whereas it is much higher in this other container here. Since these two have different shapes, the amount of water or amount of sand that you can fill at a given energy level or a given height is very different in these two cases. Therefore, even though the probability of occupancy is the same at some height level, so same height level I take here with respect to the ground position, if I take the same height level, in both cases the probability of occupancy is 1 given the height levels that I have chosen, probability of occupancy is 1, but the shape of these two containers is different. Therefore, the actual occupancy, which consists of the probability of occupancy plus the number of states that is available inside this system, that actual occupancy is different for these two states, okay. So that is a very different piece of information, and therefore where it fills up, where it runs out of particles is very different for these two conditions. So therefore keep in mind that the shape of the container is also very useful, is a very important piece of the information that we need, and with respect to the system that we are talking of, that is the number of states available at each energy level. Okay, so that is a very important piece of information that we have not included in the discussion. So that is something that we will get to later, but still the definition for Fermi energy is something that we are now clear about. It is the highest energy state that is occupied at a temperature being equal to 0 Kelvin, and at any other temperature it is the energy state where it is the value of energy at which the probability of occupancy is 0.5. So these are the two definitions that go with the Fermi energy. And is something that we become familiar with. The Fermi energy is of importance because it represents the highest energy level available in the system, which is occupied by electrons at 0 Kelvin, or probability being half at any higher temperature, and therefore in some ways is the energy value around which those electrons are now available to interact with higher energy levels. Okay, so for example, we will see in our next class, we will discuss this in little greater detail. As you raise the temperature, okay, so as you raise the temperature, you see that only it still remains, probability of occupancy, it still remains close at 1 or very close to 1, all the way to some energy level that is close to the Fermi energy level. Only at energy values which are very close to the Fermi energy level, you start seeing a probability of occupancy that drops from 1 for values below E equal to Ef, and goes up from 0 for values above energy above E equal to Ef. So in fact when you raise the temperature, it is energy values which are close to Ef that sort of participate in the process of the change in temperature, okay, and that is a very important information that we will look at. Not all the energy levels seem to participate in the process of the gain in temperature. The temperature of the system has gone up from T0 of 0 Kelvin to some other temperature T1, which is greater than 0 Kelvin. So the temperature of the system has gone up, but if you look at this figure, the way I have drawn this figure, which is consistent with this function here. So if you take this function and you plot it up in any software that you are comfortable with, you will find that this is true. This kind of a picture that I am drawing is essentially correct. So what we find is only energy values which are closer to the Fermi energy level seem to be participating in this process of change in temperature. The greater the change in temperature, more the number of energy states on either side of Ef which seem to participate in the process. Okay, so that is a very important piece of information. More specifically, there are a large number of states which are away from the value of E equal to Ef, which do not in any manner in any significant manner participate in this process of change in temperature. Okay, okay. So they all the energy values which are below this, for example at this at T equal to T2, the probability of occupancy is still 1, and as long as the probability of occupancy is still 1, they are not actually participating in this change in temperature, okay. So they are largely oblivious to the change in temperature for the entire system. So that is how this behavior is. So most of these energy values are not participating in it. Similarly here it is at all values below this energy level are not participating in change in temperature. So for a set of fermions, that is a very important characteristic of a set of fermions. The set of fermions, a collection of fermions if you have, and which is what we are talking of as the collection of electrons present in a solid, and if you take that collection of fermions, given the characteristics of the fermions, they come up with, they are following all the things that we have just described here, and therefore this diagram, and therefore this diagram represents what behavior they are demonstrating to us. And when you have such a diagram, it is telling us that those fermions show all these kinds of behavior, that not all of them participate in an energy change process, only some of them are participating, okay. So so this is the Fermi-Dirac statistical distribution. We have derived it in the last couple of classes. Today we have looked at various features of the Fermi-Dirac statistic distribution. We have looked at Fermi energy, we have looked at a plot of the Fermi-Dirac distribution, we have tried to see what that plot implies as a function of temperature, what the plot implies as a function of energy, what is the significance of the highest energy level that is occupied. We have designated that as the Fermi energy. We have briefly considered what is it that I mean, okay, we have designated something as Fermi energy, so what, I mean, why is it of any significance? We said that it is the borderline between what is already fully full and what is empty, and therefore that represents the border over which, across which all the transactions are occurring, so to speak, okay. So therefore it is of some significance. We will discuss in the next class what is the although I have described to you here in this plot that what is happening across that Fermi energy level as you change temperature, what is the implication of it, we will see in our next class, but that is the characteristic of it. So all the major features of the Fermi-Dirac distribution we have looked at and we have examined. I have also highlighted to you the information that is not available in this Fermi-Dirac distribution, which is the actual number of states at each of those energy levels, which is corresponding to the shape of the container if you are looking at an analogy of pouring water into a container or sand into a container. So this then is the summary of what we have discussed this class. Next class we will take up, we have done all this discussion because we wanted to make an improvement to the Drude model, and hence came up and decided to look at the Drude-Sommerfeld model, which came up as the next improvement on the Drude model, which used the Fermi-Dirac distribution, and therefore we have looked at this. So in the next class we will directly compare the Maxwell-Boltzmann distribution, which was used by the Drude model, with the Fermi-Dirac distribution, which has been used by the Sommerfeld model, and in this comparison we will understand in what way the Sommerfeld model has actually improved on the Drude model, and from there we will look at further possibilities of improvement and other features of the system, okay. So with that we will halt for today. Thank you.